Welcome everybody. In the next few videos we are studying and are being upset by the strange behavior of the electron. This is not the classical way or the historical way to introduce quantum physics, because then you would have to start with Einstein's light quantum hypothesis and the photoelectric effect. But in my experience, this is better suited because it breaks even harsher with our classical models that so far we had about particles, so-called particles. So when I ask you what is the electron, all of you I think would say, well, it's a negatively charged particle and it's very, very tiny and maybe even spherical. At least when I think about a classical electron, I think of a very tiny sphere which is negatively charged. And we all think, well, we do know electrons. They make up electricity that we use every day. And we were able to accelerate electrons using electric fields and to change their direction by using either electrical or magnetic fields. And we have actually seen the electrons travel along curves like a parabola between the plates of a capacitor, or in circles in the magnetic field of two Helmholtz coils. So we think we have a pretty good picture of the electron. But now we are discussing some experiments where the electrons behave very, very strangely, to put it mildly. So we start with Electron-diffraction, in German Elektronenbeugung. Recall, I would recommend watching the video on this stuff here. In the 1910s, 1912, 1915, famous physicists Bragg, father and son, Max von Laue, Debye and Scherer and others used X-ray diffraction to study the structure of crystals. So they shot X-rays at crystals and there were diffraction and interference patterns, and you could evaluate them and thereby understand the structure of crystals better. Now in 1927, two physicists by the names of Davisson and Germer did something crazy, apparently crazy. They did the same, but they didn't use electromagnetic waves, for example X-rays, but they used an electron beam. So here's a schematics of the modern version of this experiment that we are actually going to do. So we have an evacuated glass tube. Inside that glass tube is a hot cathode that is being heated by small voltage and thereby emitting electrons by the Davisson effect. Then there is a high voltage, high potential difference between the cathode and the anode. About 3,000 to 5,000 volts give you good results in this experiment. And then there are some metal devices to focus the electron beam. I'm not going into details here. The wiring is also left out. This is simply there to get a thin electron beam that I can point at the anode. Now in the anode there's a little hole, and over that hole there is a thin graphite foil. It's actually very, very thin, a few atom layers thick only. This, I don't know if this is the correct English word. It's polycrystallinous, meaning it's pulverized, or there are many, many microcrystals inside it, scattered inside this graphite foil. Historically, those guys didn't use a graphite foil, but they used a nickel crystal, which served as a reflection grating for the electron beam. All right, so what would we expect? So here we have a close-up version of this graphite foil with a lot of little graphite microcrystals inside, and very, very thin, so that the electrons actually have a chance to pass through and are not completely absorbed. So if electrons really were those little bullets, those tiny charged spheres that we shoot at this layer of crystals that are arranged in a random way, then one would expect that they are scattered in all directions. So they should meet this screen like homogeneously everywhere. This screen here lights up green whenever an electron hits the screen. So you can actually see where the electron lands. And if this were true, that electrons really do behave like little bullets, then the whole screen should light up greenly. Well, let's take a look at what actually happens. So here's the actual electron diffraction tube of the physics department of my school. Here you see the glass bulb, highly evacuated glass bulb, and here is the fluorescent screen. Here you see the power supply. This down here is for heating the cathode, and this here generates the high voltage that I need to accelerate the electrons. It goes up to 5000 volts. Here's a close-up look at this part of the tube. Back here you don't actually see that is the electron gun, but what you can see is the tungsten, in German Wolfram. The cathode is made of tungsten, and here's some tungsten evaporated, and it can be seen on the glass. This part here is the electronic optical system that focuses the electron beam. So you end up with a very tight beam that hits the cylindrical anode here. And there's a hole in the anode, and on there is a very fine nickel grating, and on that grating there is the graphite target, a very, very thin layer of polycrystalline graphite that has been deposited there by vaporization. And here the magic happens. And here you see the shocking result. The screen is not illuminated homogeneously, but we clearly see a diffraction pattern. At the location of the bright rings, a lot of electrons hit the screen, and in between, this dark green means almost no electrons hit the screen. And here in the middle, I have a very bright spot because a lot of electrons simply fly through the thin graphite foil, and also you could call it the maximum of order 0 because there also will be a maximum of the diffracted part of the beam. So let's have a look what happens when I turn up the voltage. The rings become smaller and smaller, and now I'm at about 5000 volts. The rings merge into one. At least you can tell the difference between the two rings, but still it's very clearly a diffraction pattern. And now to prove that I haven't cheated and used X-rays to produce this diffraction pattern, I use this bar magnet here, and we will see what happens when I move it towards the screen. So you can clearly see that the pattern gets distorted, which is due to the Lorentz force of this magnet acting on the electrons of the beam. So these are real electrons. And this experiment clearly shows that electrons, which we thought of as classical particles, are somehow able to display an interference pattern or to get diffracted. So I'll be damned. There is actually diffraction and interference. And they obtained similar results, as I said before, not with this exact same setting, but they also found out that there is interference or diffraction. This is very, very strange. It gets even worse. First of all, you can do a similar experiment by taking a thin aluminum foil and then bombard it with either X-rays or a highly energetic electron beam. Let's take a look. This is the diffraction pattern using X-rays. We already expected that, we discussed that. This is what the Braggs and the others already did. But now let's take a look at the same aluminum foil when using an electron beam. It's also very clearly an interference pattern. The radii are a bit different, but still it's very, very clearly an interference pattern. And even worse, well, here with electrons you could always say, all right, the electrons are charged, so maybe they influence each other and fly only to certain regions of the screen. That might be possible, right? Well, then let's take neutral particles. When you take neutrons, they are way more heavier than electrons, about a factor of 2000, and they carry no charge. And In this experiment, I don't take a beam of many neutrons, but I take one neutron after the other. So I shoot a neutron at, I think it's a copper foil in this experiment, a thin copper foil. And now look what happens. Bam! That's also very clearly an interference pattern. You also see that the neutrons arrive at the screen actually as little particles. They make these little dots, these little spots here. The bright spots are where a lot of neutrons end up, and the dark regions are where very few or even no neutrons end up. And again, one neutron is shot after the other, so it's completely impossible that they make any kind of interaction on their path. Welcome to the quantum world. This is the strange behavior that quantum particles actually show, manifest. Okay, now let's take a closer look at the actual experiment that we did. We are discussing in some depth the results of this electron diffraction tube experiment. Here's a close-up version of the important parts. Here we have the electron gun, which shoots out a beam of electrons. Then here, this is supposed to be one graphite microcrystal inside of the thin graphite foil. And this microcrystal should have an angle θ1 such that here, under the angle of 2 θ1, because this is important, here I already have θ1, and then the reflected beam also has an angle of θ1. And this angle should be such that I observe the first maximum here on my screen, so the inner ring. As we have seen in the experiment, there are actually two rings, so you could think, well, of course, this is the maximum of order 1, and then comes the maximum of order 2. This is not true because of the special structure of the graphite crystal lattice. I tried to draw part of it here. There are actually two different lattice planes that can give you diffraction effects. One is, if you look in this direction, you see these atoms here. Those are all carbon atoms, each in a perfectly regular hexagon. And if you put these together, you get graphite. This is one layer of graphite. There are a lot of layers. Actually, in the pencil that you're using, there are a lot of layers of graphite that can be easily smudged onto the paper. So if you look in this direction, you have this lattice constant, d prime, but you can also look in this direction, and then these atoms here give you a larger lattice constant. d prime is actually 123 picometers. I think you can find that out by using X-ray diffraction methods, for example. And the other lattice constant is square root of 3 times d prime. You can figure that out using elementary geometry, but that's not important. The actual value is 213 picometers. Why these here or these do not contribute, I can't tell you. I actually do not know enough about crystallography to tell you why these aren't relevant. And here, of course, you have the same d if you observe these layers, but why these layers here, these parallel layers, are not important, I cannot tell. So this explains why we saw two rings. They are actually both maxima of order 1, but with different radii corresponding to these different lattice constants. And we are going to be working with the inner maximum, with the innermost interference ring, not the maximum of order 0, of course, but here of order 1. And this one corresponds to the larger constant. The larger here, this constant, the smaller the diffraction effects, same as in optics. So the smaller radius corresponds to the larger d, in this case 213 picometers. Then the distance between the graphite foil and the screen is 13.5 centimeters. And then you actually measure the radius of the inner interference maximum. And now there's a little mistake, because This here is the distance from here actually to the screen, but here, this first circle here has a bit of a smaller distance to the graphite foil. But actually there's no information in the experiment description about this error, or even about here the radius of the sphere, or where this is. It's not in the middle of the sphere, obviously. So we are making a little mistake, but still the results are astonishingly good. So this doesn't really seem to matter. So in your calculation you are using this rectangular triangle, and you simply assume that this length is about 13.5 centimeters. And it's actually not that easy to get an exact value, because as you saw, they have a bit of a width, and the screen is curved, so these values are as good as it gets. But again, still the results are astonishingly good. Okay, we already talked about this, and now for the experimental data. When you use a voltage of 3000 volts to accelerate the electrons from the hot cathode to the anode, then the radius of the first interference ring is 1.4 centimeters. If you turn up the voltage to 4 kilovolts, then the radius gets smaller. The radius is 1.2 centimeters. And if you turn up to 5 kilovolts, you end up with about 1.1 centimeters. And now these two columns are very, very important. Now we're taking a bold step. We are actually seeing an interference pattern. It's about the same as when X-rays were used. So we simply assume that the Bragg law of X-ray diffraction also holds for electrons. And in this law you will find a wavelength. In the Bragg law, in the Bragg condition, there's a wavelength. And now it's your task to actually calculate to which wavelength these numbers here correspond. This would be a very good exercise if you want to try it on your own. I'll give you some hints, then you can pause the video if you want to, and afterwards we are talking about it together. You are using Bragg's condition. You can use this data to find out what the angle θ1 is, and then you simply plug it into Bragg's condition and get a wavelength in the picometers. And even more importantly, you have to compute here the wavelength times the momentum, in German Impuls, of the electrons. Y is completely mysterious right now. I'm going to talk about that later. But this will give you a very, very important constant. It should actually be about constant. And this here is the classical momentum. So mass of the electron times its velocity. And to compute the velocity, you simply use energy conservation. Here it has potential electrical energy, and then arriving at the anode, it has kinetic energy. It takes energy from the electrical field. So try to do this calculation as well and see what you end up with. Good luck. I'll see you soon. Okay, here are the results. We are going through the calculations step by step. As I already mentioned, we are simply using Bragg's law without knowing why this should make sense for electrons, or even if it does make sense, but still we use here Bragg's condition for the first interference maximum. This path difference to d, for d we're using here the larger constant, times the sine of the angle θ1 must be 1 times the wavelength. Again, whatever that may mean for electrons. And using trigonometry and the approximation, or the little error I talked about, the tangent of 2 theta is approximately r1 divided by a. So from this it follows that θ1 is the arctangent of r1 over a divided by 2. I plug this in here, use my calculator, and end up with these wavelengths. They're about the wavelength of X-rays. That is why we have almost the same interference patterns here. So we have 22 picometers. Pico is 10 to the minus 12. Here we have 18.9, 19 would also be okay, because you see here we haven't done very exact measurements. I think 19 would give you even a better constant here, and here 17.3. Now this product turns out to be very important. To calculate the classical momentum, you need the velocity of the accelerated electrons. For this we use the energy conservation law. The potential electrical energy that is stored in the field between the cathode and the anode is charge times voltage, so E times U. And this is equal or gets transformed into the kinetic energy of the electrons. So this is the classical formula, 1/2 times mv squared. You solve this for v, and then the momentum is m times v. Then you can write m as the square root of m squared and pull it under the square root and then cancel 1m. Makes it a little bit easier to type into your calculator. And then here are the constants you need. The elementary charge of the electron is 1.6 times 10 to the minus 19 coulombs. And the mass of the electron is 9.11 times 10 to the minus 31 kilograms. If you calculate these momenta and multiply them with the wavelength you obtained here using Bragg's condition, then Planck's constant pops out. And this here is spectacularly good, for remember, these weren't very exact measurements and we made these little mistakes here. But still, for such a simple experiment setting, these are very good results. So the average is about 6.5 times 10 to the minus 34. This is very, very good. So what can we conclude from this spectacular experiment? Well, we can definitely conclude that electrons can display wave-like behavior because they can generate an interference pattern, and this is a classical wave behavior. And then I can associate to these patterns here a wavelength, blindly using a condition that we know is true for electromagnetic waves. Here I'm not sure, my English fails me, associated to a wavelength, maybe better than with, I'm not sure. You get the idea. And many further experiments show that actually this is always true. If I take the wavelength from any interference pattern that electrons or even other elementary particles display, and take the product with the classical momentum, this is very strange. This bothers me up till today, because here you take a clearly classical value for the momentum, mass times velocity, both calculated or measured in a classical way. Then you get the constant of the quantum realm, Planck's constant. In German, das Planck'sche Wirkungsquantum. 6.63 times 10 to the minus 34 joules times second. Now, a French physician, Louis de Broglie, actually postulated 3 years before these experiments were done for the first time that every matter particle, like electrons, protons, neutrons, should have a wavelength. And he postulated this wavelength should be given by h, Planck's constant, divided by the momentum. He got to that formula because for light, as we are going to see later, this formula holds. I can associate a momentum to light, as strange as it sounds, and then this relation here holds. And de Broglie said, well, this also holds for matter. Again, without experimental data supporting his claim. And he actually was awarded the Nobel Prize for this. This is famously called the de Broglie wavelength, and this is where this formula actually comes from. No one got the idea in the first place to say, well, I take the wavelength times the momentum, whoa, Planck's constant pops up. But I think it was because de Broglie already postulated that this should be so. And he talked about matter waves. Now, this is a very dangerous expression that I'm trying to avoid. It is not true at all that the electron spreads over a region of space and dances around like a wave or moves along a sine curve or whatever, all the classical notions that you could have about waves are not true for the electron. And we are going to discuss in depth what this wavelength actually means for the electron. So do not jump to any conclusions, and please avoid using this word matter waves. All right, that's it for the electron diffraction. In the next video, we are going to discuss the most beautiful experiment of all times, the double slit experiment with electrons. Thanks for watching. Hope to see you again, and bye-bye.